Okay, Assalamualaikum and good morning. So today we'll continue with our lectures, but before that, there were the discussion about the test. Sorry, test one. Not going to test two yet. Test one. So I believe everyone has agreed to shift this to next week, which is let me next be sorry. Next week will be the 29th. Is this okay? Okay, so our test one on the 29th instead of tomorrow. Okay, so I've also given you the link to the folder to submit your assignment one. So everyone has to submit individually. So I will close the folder around 5 p.m. Today. Okay. So let me start with the lectures. So let us recall what we did last week. So we have essentially started to discuss about tensors and special relativity. So let me just check where we have stopped. I think we have introduced metric and inverse metric. Also the index lowering and raising. And yes, this is perhaps one of the main things that you need to understand in special relativity, that your vectors, your four vectors, will be classified into three different types: space light, light, and time light. The usual events for ordinary particles will be following a time-light vector, and for photons they will actually follow a light vector. So we'll talk about this more later on. And then we talk about tensor equations and symmetries. So we already mentioned that, okay, generally a tensor equation, if it's valid in one particular reference frame, it will also be valid in another reference inertial frame. Sorry. So and then we do symmetrization and anti-symmetrization. So these are things that you should know. And finally, we introduce alternating tensor for four-dimensional Minkowski spacetime, which is a bit different from the ones that you have seen for the classical mechanics. Particularly, you have, of course, you have the four indices instead of three, but particularly you'll find that your upper index alternating tensor is actually having a different what we call definition from the ones with the lower index. Okay, so so we have gone through this and we talked about the symmetries of tensors. So we will look at one particular example for which it's an important example for which the tensor that's involved is actually antisymmetric. Let me check if the person is coming in. Okay, I think the auto admit is okay. So get back to this. Okay, so essentially one of the important tensors that we'll be doing, in fact, in the second part of the course, is the so-called electromagnetic field tensor. Okay, and if you remember how essentially when you do electricity and magnetism, for example, in probably one of your earlier courses, you find that somehow the electricity and magnetic field are interrelated. So for example, an electric current carrying wire produces a magnetic field. I think this is using a right hand rule or something. can't remember now. That was a long time ago. And then if a wire in motion cuts a magnetic field, then it will generate an electric current inside your wire. Okay, so somehow this ability of having this relationship between electricity and magnetism uh, tells us something that okay, there's something essentially intertwining this idea of electric field and magnetic field. So and this is so when you go to relativity, and the way it's been described is essentially by this tensor. The tensor is totally antisymmetric, meaning okay. First of all, sorry, the tensor is of rank 2, and here is written in terms of covariant rank 2 tensor, which is totally antisymmetric. Okay, and the components of the tensor as it is. No, I'm just giving you the form of that tensor. We'll talk about this more later on when we talk about classical fields. So essentially it's given by this matrix, and you can see that okay, if you remember that your last component is your fourth component. So this is actually this is the fourth column, and then the fourth row. Okay, and they are related to your electric fields. And then the one sort of off diagonal part, this triangle version, is essentially your magnetic field. And also the lower triangle here is also the magnetic field, and their relation is related by the fact that it's totally antisymmetric. Okay, so we'll give this a definition later on when we'll talk about the classical fields. But for now, we are just introducing this as part of an example of a totally antisymmetric tensor. Okay, so one can actually see how this works out when you write down the components in terms of the components of your field strength tensor. Your F is called field strength tensor. And the way the component works, as I said, for example, over here you have your fourth column, okay, your F14, F24, F34. In fact, they are related to your electric field. So you can see that F14 is actually E1, F24 is E2, and F34 is E3, or generally I can say EI equals to FI4, where I equals to 1, 2, 3. Okay, so this is quite easy in terms of its definition. But for the magnetic field, it's a bit, well, I mean, you'll see later on why this actually in this particular form. But for electric, so your magnetic field, it gives you your components of your magnetic field as if it's not quite, no, they have all different indices over here. So B1, for example, is actually F23. So the index 23 is not appearing here, but that's the way it works. Okay, so you have B1 equals to F23, B2 equals to F31, and B3 equals to F12. And you can actually see some kind of a cyclic symmetry that you have seen in the case of your epsilon tensor before this. Okay, your epsilon ijk has this idea of permutation, and then it has a cyclic symmetry kind of thing. So one can use that particular fact to actually rewrite your vectors, the component vectors for your magnetic field in terms of this epsilon ijk. So in fact, it's now written as Bi equals to half epsilon I jk fjk. So you can see that here is your free index, okay, and then these are your dummy index. So it's been summed in this particular case, okay. And you can check that this actually works. So if I have, let's just take I equals to 2, so I would have B2 half epsilon 2jk f jk, okay, and that will give you, if you try to sum what are the possible indices that can come in this jk combination, since you have already 2 here, so remember that 2 cannot be in this jk position, because otherwise it will be 0. So that means it's either 1 and 3 or 3 and 1. So let's write those. Epsilon 231 f31 plus half epsilon 213 f13. Okay, and if we check, epsilon 231 is just 1, so that gives you half f31, and epsilon 213 is supposed to be minus, so that gives you minus half f13. But then you know that f31 and f13 is essentially minus of each other, so I can write this as f31, okay, which is essentially this quantity, okay. So you can do for the rest, and then you can check that it works. Okay, now as I said earlier, the fact that your vectors of electric field and magnetic field are actually sort of embodied in this new object called a field strength tensor. So they are actually part of a single object, okay. So that tells us, okay, the relationship between electric field and magnetic field is quite close to each other, okay. And one can actually switch the roles of your electric field and magnetic field by defining what is called a dual tensor to this field strength tensor, which is denoted with this asterisk or star on top, showing is actually the dual of that, and it's still a rank 2 tensor, coherent rank 2 tensor, but it's been defined using your alternating tensor in 4 dimensions. Okay, so that means I will have epsilon mu nu, the free index over here. So here the free index, and then the next 2 index will be a dummy index, and that has to be contracted with the f rho sigma. Okay, and this is also totally antisymmetric. Okay. Because your epsilon here is antisymmetric with respect to your mu and nu here. Okay, so you can see that, okay, if I exchange your mu and nu, I will get a minus sign here, and this now becomes just another definition for your dual tensor, but with nu and mu exchange. So that tells us, okay, it's totally antisymmetric. Now with a little bit of work, you can actually show that that this in terms of components are related to an earlier components of your field strength tensor. Okay, let's just work one of them, and you can try the rest. So let's consider F12 star. So just like the case of your magnetic field now, So I'll just substitute 1, 2 for mu and nu, and then rho sigma will have to be sum over all possible combinations. And because there's already 1 and 2 here, that means this can only be either 3 or 4. Okay, so that gives us this only two combinations, epsilon 1, 2, 3, 4, and epsilon 1, 2, 4, 3, and 3, 4 here. You have F34 there and F43 here. Okay, so that gives us, if you check the previous definition of epsilon 1, 2, 3, 4 is 1, and 1, 2, 4, 3 is minus 1, so I get that. And remember that your F over here is, okay, we have not really introduced this F, but it's also, no, this is the contravariant version of your field strength tensor, F mu nu. Your previous, the one that we have actually defined is, here is the covariant case, okay, and it's similar in a way. This is totally antisymmetric, and this is also totally antisymmetric. How you actually do this is essentially you raise your indices using your Minkowski metric. Okay, so in other words, F mu nu in general is eta mu rho eta nu sigma F rho sigma. Okay, so that's how you define your contravariant case from your covariant case. Okay, you just raise the index of your rho and sigma here by mu and nu here. So you can find out what this is essentially, but the essential point, this is also antisymmetric with respect to mu and nu. Okay, that needs a little bit of convincing here. Maybe you can do the exercise. But so that tells us, okay, your F34 and F43 are minus of each other. So this one can be combined into F34, and F34, as I said, is actually just that. Okay, and essentially, if you look at what is possible here, here is 3 mu. That means the only non-zero case is when mu equals to 3, and here is eta for nu. So the only possible value for nu for the non-zero case is when nu equals to 4. So then you see that this is eta 33, which is 1, eta 44, which is minus 1, and then this one should be F34. Okay, so you get minus F34, which you can again swap the index, that because of the antisymmetry, you get this to be plus F43. Okay, and what is plus F43? If you look, F43 is what? This. Okay, so it will be this. Okay, this is the fourth row and the third column. Okay, so you find that this is essentially your F12 star is minus E3. Okay, and then you can do the others. Okay, so just now we are looking at F12 star. So F12 star is now actually here. Okay, and you can check for the others. Okay, this I just summarize everything here, and you'll see that what happens previously it was the electric field in this fourth column. Now it becomes the magnetic field. Okay, and then the fourth row is also the magnetic field, but now with a minus sign because of the antisymmetry. And on the triangle, the upper triangle and lower triangle, here is your electric field, replacing the ones that we had for your what you call magnetic field before. Okay, So in other words, the dual operation is actually equivalent by making an exchange between your electric field and magnetic field, and your magnetic field becomes your negative of electric field. Okay, so it's a bit strange in some sense that you have this minus sign, but remember this comes from the fourth column and the fourth row. Okay. So, okay, that sort of gives you a feeling of an example where you have a totally antisymmetric tensor, and it describes a physical thing, which is essentially your electric field and magnetic field in one single object, and this particular object is actually invariant under you know, invariant under Lorentz transformation, but of course the components may change a little. We will see later on how it changes when you do the classical field topics. Okay, so for now it's just written as an example of this antisymmetric tensors. Okay, so that is essentially what we have for lecture 7 notes. Okay. Any question at this stage that you want to ask? I guess no. So let me just continue then. So the thing that we want to do essentially is how we apply this Lorentz transformation to tensors, and give some of the things that you probably see in discussion of some maybe some astrophysics kind of phenomena. Okay, so the idea here is essentially we look at how changes of reference frames actually give you what we call a Doppler shift, and then also the aberration that we have actually discussed at some point when we did the velocity addition formula, if I can recall correctly. Okay, so we have done aberration before, so we'll reproduce this in the sense of performing these transformations on tensors instead. Okay, so the first thing that we need to actually describe is essentially a wave. Okay, the wave will come from some electromagnetic signal. Okay, we'll see in a minute how we define this. So this wave normally a monochromatic wave. Okay, and given the kind of objects that we see is actually from a distant object in space. So normally when it reaches to Earth, it will be in the form of a plane wave. Okay? And plane wave is described as this sinusoidal function. Okay, so remember your Euler formula, EIX equals to cos x plus I sin x. Okay, so we are just taking the real part over here. So that corresponds to the cos, and but when you do that, one still can have a general description by introducing this so-called phase angle. Okay, this is just giving you how you actually allow what possible different phases when it starts at the origin. Okay, so for example, a different one will be something like this. Okay, so your origin is actually well, I mean the start of the wave actually begins at a different point in the reference frame. Okay, so that allows still a general description. So But the point that we need to highlight here is your form for your plane waves that you have actually seen before, in terms of cos kx minus omega t. I believe you have seen this before in some lower courses. That can be generalized in 3D as follows. Your kx is only for one dimension here, so that means you will be able to find components of k for each x, y, and z coordinate. So you write this as k dot r. Okay, and your k is essentially what is called the wave vector. Okay? So the wave vector essentially tells you how the wave is actually moving with respect to the x, y, and z axis. Okay? And normally one has a relationship for this k with this omega here. Okay. How should I see? Probably it's best to start from this. Do I have it down here? Probably not. So let me just do it from the beginning. The normal thing that we actually have is essentially you have the speed equals to the frequency times lambda. So in this particular case, you are describing light. So the speed is actually c. Frequency, we normally write this as nu, and then your wavelength is lambda. Okay, so I believe you have seen all this one before. But now what we can try to do is to introduce this angular frequency, and the angular part for your lambda is going to be your k. So this would be what 2 pi omega, and then your k, if you remember, sorry, maybe I should do this differently in a different equation. So omega is 2 pi nu, and your k is 2 pi lambda. Okay, so you introduce this angular version of your frequency and wavelength. Okay, actually this is not the angular version of wavelength, but it's called a wave number. So if you look at this, then you'll actually get what 2 pi nu. Sorry. Okay. Let me write this as 2 pi nu, and then I have an extra piece of 2 pi here, so I will divide this by 2 pi, but that is just 1 over k. So this is actually equals to omega k. Okay. So in other words, there's a relationship, it's called a dispersion relationship, saying that your angular frequency and your wave number is related by this multiplication to give your speed. Have you seen this thing before? I think if you have done quantum mechanics, you probably, if it follows my notes, then you probably have seen this before. So now we're going to generalize this as a vector. So your k is now a vector, and you can actually see now that is having the same thing. So here you bring your I'm having slightly, oh sorry, this is I'm making a mistake here. So that is really omega over k. Sorry, nobody noticed that. Okay, so then you can actually see your omega is related to k, so I can bring my k on the other side. Okay, and then you have your c over here. So you get omega over c is going to be related to k, but as a vector now, you'll see that this is only scalar. Okay, so I will have to actually write a vectorial quantity here, which would give you the vectorial quantity for your k. This is your wave vector now. Instead of your wave number, it becomes a wave vector. Okay, so the wave vector, the direction of the wave vector is given by this n, and this n essentially tells you how the direction of your wave propagation. Okay, so we also have this condition that this n is just a unit vector, just showing this particular direction. Okay, so then we have actually generalized this to the vectorial quantity k, and the relation between the wave number and the wave vector is just the magnitude. Okay, so you get back to the things that we have seen before. So now what happens is that, okay, we want to understand this a little bit more properly in the context of special relativity, and you can see that, okay, this is quite nice in the sense that over here I have my three-dimensional spatial coordinates, but over here you have your time coordinate. But according to special relativity, they should be considered as a four-dimensional thing. So I should be able to write this in a better way, so that, okay, I can actually see this. So then, so let me write it this way. So I will have something like this: the components of k multiplied by the x, y, z position. Oops, sorry. I'm just worried when this auto admit doesn't work. So it does work. Okay. So this will give you the k dot r thing, but now the fourth component, you remember, if you want to make sure that your fourth component has a spatial dimension, that requires us to have your time multiplied by c. Okay, but you don't have c over here, so that means I will need to put omega over c, and then that will cancel off, and then you get your k dot r minus omega t. Okay, so that, if you can see, so if these are the the components of the vector in 4 dimension, okay, then this should be also components of your vector in 4 dimension corresponding to your wave vector. So we define this wave vector here in this way. We rewrite the ones above by a 4-dimensional dot product, in some sense, the inner product, k mu x mu. And remember that we always maintain your position is actually given by a contravariant vector. So when it contracts over here, it has to your k mu has to be a covariant vector. Okay, so x mu is r ct, and k mu will have the wave vector, and then your fourth component is given by minus omega over c. Okay, so the whole thing now is written as that. So with that, you are able to describe how waves actually being written in a relativistic sense. The one that's important is the argument instead of the the form of the function itself. This could be a different function, but the thing inside here should be a scalar. Okay, so k mu x mu is a scalar, which it should be for phase. Okay, so the whole thing is actually, we call it as a phase. Okay, so now one can start to think of, okay, how does the what you call if you move to a different reference frame or inertial frame, okay, how would the wave being described differently? Okay, well, it's just the thing in the argument of this cosine function, for example. So if I go to the reference frame that uses the dash coordinate, so I will have this transformation coming in. Okay, so this actually is the inverse case because I'm going from x mu and dash version to the dash version, and then that would tell us, okay, I will have this inverse Lorentz matrix, okay, multiplying this k mu, and that tells us, okay, this is how your covariant vector transform. So this will be k nu dash x nu dash, and then alpha is just a constant. Okay, so your k mu is actually a covariant forward. And remember that, if you remember, it seems a bit funny to have this minus sign over here. Well, this is because you had your covariant vector for your wave vector defined first. But if I wanted a contravariant case, then you'll see that no, this is much more natural in this particular context, because when you do the contraction or the index raising of your k nu here to k mu here, your minus sign will fall off because of the minus sign inside your eta. Okay, and this is called essentially the wave forward. Okay, let's move. So now let's consider a kind of a wave moving from one point to another point in space and time. Okay, so it goes infinitesimally. For example, this is one event. Here's another event. Okay, you have to remember now we are talking about space and time together. So you talk about space and time coordinates together. So this event occurs at x mu. This event occurs at x mu plus delta x mu. Somebody coming in this hour. Okay. As you know, when we do we make comparison, for example, from one wave to another, a wave at one point to another point, we are always interested to see the phase difference. Okay? So the phase difference is just given by your k mu multiplied by the coordinates of the event. So here's the event over here, and then the difference with the k mu contracted with the position of this event over here. Okay, so essentially you'll see that your phase difference is actually a scalar. Okay, so what does that actually give? So so in other words, being a scalar, this quantity is the same in any reference inertial frame. Okay, and what this corresponds to is just you can think of it as the number of wiggles inside this particular length, or number of waves between events. Okay, so okay, so that's one thing out of the way. The other thing that we need to also know is the fact that the magnitude of the wave forward vector is given by the contraction here. Okay, and over here one has to recall what is your k1, k2, k3, and k4. So it will give you k dot k minus omega squared on c squared. But if you recall what is k squared, so k squared will be your magnitude of your wave vector in 3D minus omega squared on c squared. So if you remember the earlier thing that we did, your omega and k is written in this way. So if I were to rearrange that, okay, so what was it? I can't remember. It was c equals to omega over k. So right. So in other words, over here, let me just write that down so before I forget. C equals omega over k. Over here now, these are all scalars, so you can think of this as magnitudes now. So if I were to write this, then I will see that your k equals to omega over c. Okay, so this is the magnitude now. So k squared is actually omega squared over c squared. So in other words, this quantity is going to be equal to 0. Okay, so in other words, k mu is essentially a null vector. Now, it actually makes sense because remember that these are supposed to be telling you how the light propagates, your k mu. Okay? So, and your k mu will actually follow the I should say the curve that's supposed to give you the light rays. And the light rays, if you remember, would actually belong to, so let's consider this as a position of a photon, okay, propagating through time. Then h mu have to be equal to 0, because h squared equals to c squared t squared. Okay, so in a way this makes sense. Your k mu here is 0 is actually corresponding to this light rays forming this sort of position squared equals to c squared t squared. Okay, I hope that makes sense. All right. So now one can start to think of, okay, let's consider, for example, a wave so traveling with respect to a stationary frame and a wave traveling with respect to a moving frame. So for this, then you can actually use a Lorentz boost transformation. So your Lorentz boost transformation is actually given by this form. This is a Lorentz boost in x direction. So in other words, remember the first position and the first row and the first column, okay, correspond to the x quantity, and the fourth column and fourth row correspond to the time quantity. So you see that the only thing that changes are your x and t's. Okay. So let's see what happens to the wave vector itself. So, and in this particular case, let's look at the case of the fourth vector, the fourth component. So you find out your k4 dash will be transformed according to L4 dash nu k nu. And remember that my Lorentz transformation, I'm limiting it to this particular boost transformation. So the only non-zero or non-trivial case is coming from your first column or first column or fourth column. Okay, so that is giving you L4-1 K1. Okay, and the other one from the fourth column, actually I want the fourth row, so this is the fourth row, and the fourth row first column, and fourth row fourth column. Okay, so that gives you L4-1 K1 and L4-4 K4. Okay, so let's plug in what we have in this particular case. Then you see, you remember that K mu is given by the vector K omega over C for the contravariant case. So this gives you K4 dash. So K4 dash gives you omega dash over C. C is just a constant. Okay, it's the same thing. C will be the same in all reference frame. So the only thing that changes here is your omega here, and then your K1 over here will be the first component of this wave vector. Okay, and then your fourth component over here will be again omega over C in the undashed frame. Okay, so now you can actually see how they are related to each other. Now suppose that we the Boost transformation is saying that our dash frame is actually moving in the direction of x with some velocity v. Okay, so v here is in terms of components given this way, so you get v00, for example. So then you can actually write down your vk1. vk1 actually appears here. It's actually v dot k. Okay, and then v dot k, you can write this in terms of your omega. Remember, your k is omega was for your light wave. Okay, omega over c times n, so I get omega over c v dot n, and v dot n, remember that n is just a unit vector here, so you get remember this formula that you learn in school, a b cos theta. So your theta is the angle between a and b, so theta here is between the angle of v and the direction of your propagation, your n. Okay, so I get my magnitude v here, and then your modulus n is just 1, and that's and we are left with this cos theta. Okay. So that gives you a general formula of how the angular frequency behaves in different reference frame. So this is essentially what we call the general Doppler shift. Okay, which is given by this particular formula. And then if, for example, you have the case where the frame is actually traveling together with the wave, that means theta equals 0, then you actually get this particular formula, which is saying that, okay, this is the factor that you have seen before. This is what we call the K factor. The one that we seen before probably swaps the plus and minus sign. So this is just saying that, okay, you're looking in terms of a direction of opposite sense. Okay. So if you have your theta equals to pi, so in this particular case, theta equals to pi would actually saying that the frame is actually moving against the wave. Okay, in opposite sense, then you actually get the k factor that you have seen before. But another interesting thing would be, okay, this is the inverse case. So I'm just changing the omega to omega dash instead. The interesting case is when you set theta dash equals to pi over 2. So in this particular case, the reference frame is actually moving orthogonal to the direction of propagation of light. Okay, and if you do that, then you actually get what we call the transverse Doppler effect. Okay, so the transverse Doppler effect is actually related by this factor 1 over gamma here, and this is also related to the idea of a time dilation effect in terms of the period of the oscillation of the wave. Okay. Let me see what else. Maybe I should continue this since we have only 3 minutes left. Maybe I should continue with this discussion probably in the next lecture tomorrow. Okay, so tomorrow there will be no test. Okay, the test will be postponed to week 6, and we will have a 2-hour lecture tomorrow. Okay, so I will stop here today. Let me get my attendance list. Okay, so before we go, are there any immediate questions that you want to ask? I guess no. So, yes? Okay. So if there are no questions, let's end this meeting. So thank you, everyone.
Thank you.
Okay, bye.